Consider a point charge plus Q and its electric field. Let us introduce a unit positive charge at a point P1 in the electric field of Q. As both the source charge and the test charge are positive, this unit positive charge placed at point P1 follows the path P1A in the electric field due to the repulsive force on it exerted by the electric field of the source charge. Thus, path P1A represents an electric line of force or an electric field line. An electric field line represents the path followed by a unit positive charge in an electric field. Repeating this procedure for various points in the electric field, we obtain the electric field lines around the charge. Electric field lines are used to represent the electric field of a charge or a system of charges pictorially. In fact, the electric field lines follow the same direction as the electric field vector at any point in the electric field. As any electric field line is the path followed by a unit positive charge in an electric field. If we draw all the electric field lines for the electric field of the given source charge Q, the electric field lines appear as shown. One of the most important characteristics of electric field lines is that they help us estimate the electric field strength. The relative density or closeness of the field lines at different points gives an indication of the relative strength of the electric field at those points. The field strength is stronger at places having more crowded field lines than at places where they are less crowded. To illustrate this, let us now consider two regions, A and B, of same area placed normal to the field lines in the electric field. The field lines in region A are relatively closer than those in region B. The number of field lines passing normal to an area is proportional to the magnitude of the electric field strength at these points. This indicates that the strength of the electric field at A is greater than the field at B. As the electric field strength is stronger in region A and weaker in region B, the electric field shown is a non-uniform electric field as the field strength varies from region to region. To understand the dependence of field lines on area, let us understand the relation between the area of the element and the solid angle created. For this, first let us understand the term solid angle. Solid angle is a measure of a cone. When the intersection of a cone with a sphere of radius r is considered, the solid angle delta omega subtended by the area element is defined as delta S by r square, where delta S is the area on the sphere, which is the area element cut out by the cone. Let this be equation 1. Therefore, delta S is equal to r square into delta omega. Let this be equation 2. For a given solid angle omega, the number of radial field lines is the same. At two different points, say x and y, in the electric field, which are at distances r1 and r2 from the charge, we observe that the area of the elements subtending the same solid angle delta omega will be delta S1 equal to delta omega into r1 square at x and delta S2 equal to delta omega into r2 square at y respectively. The number of field lines, say n, passing normal to delta S1 and delta S2 is also the same. The number of field lines passing normal to a unit area is equal to the electric field strength E. Therefore, the electric field strength E1 at X will be equal to number of field lines per unit area at X, which is equal to N by delta S1 or N by R1 square into delta omega, using the value of delta S1. Let this be equation 3. Similarly, electric field strength E2 at Y is equal to N by delta S2 equal to N by R2 square into delta omega. Let this be equation 4. If we divide equations 3 and 4, we see that the ratio of the electric field strengths at X and Y is equal to R2 square by R1 square. Hence, we can conclude that the electric field strength due to a point charge varies inversely to the square of the distance from the charge. From equations 3 and 4, we see that even though the number of field lines N and the solid angle delta omega are the same at X and Y, the electric field strength E, which will be equal to number of field lines per unit area, is proportional to 1 by R square, where R is the distance of the point from the charge Q. Earlier, you have learnt that the electric field strength vector of a positive charge, say plus Q, always points in a radially outward direction, and the electric field strength vector for a negative charge, say minus Q, points in a radially inward direction. Thus, we see that the electric field lines for a positive charge diverge normally from the charge, and those for a negative charge converge normally towards the charge. Let us now visualize the electric field lines for a system of two positive charges, say plus Q each. From the field lines, we can see a very clear picture of the repulsion existing between the system of charges shown. The electric field lines also help us in visualizing the electric field of a dipole consisting of charges plus Q and minus Q. We observe that the electric field lines for an electric dipole are continuous lines extending from the positive charge to the negative charge. From the field lines, we see very clearly the force of attraction existing between the system of charges in the dipole. Thus, we see that the field lines convey a very clear picture of the nature of the electrostatic forces existing in any system of charges. From these examples of various charge configurations, we observe the following properties of electric field lines. The tangent drawn to an electric field line at a point in the electric field gives the direction of the electric field strength E at that point. The direction of the tangent at a point indicates the direction of the force on a unit positive charge at that point, and hence it gives the direction of the electric field strength at that point. For the electric field created by a system of positive and negative charges, the field lines begin at the positive charge and end at the negative charge, since the field lines diverge normally from a positive charge and converge normally at the negative charge. For a single charge, they may start or end at infinity. Electric field lines do not intersect each other. If the electric field lines intersect each other, then At the point of intersection, there will be more than one direction for the electric field, which is not possible. The number of electric field lines is proportional to the magnitude of the charge. The number of electric field lines is proportional to the magnitude of the charge. For a charge configuration of magnitude Q, if the field lines per unit area normal to it are, say, n, then for a charge of magnitude 2Q, the number of field lines passing normal to a unit area is equal to the electric field strength. Electrostatic field lines never form closed loops due to the conservative nature of the electric field, since the lines of force diverge from a positive charge and cannot converge at the same positive charge. For a uniform electric field, the electric field lines are parallel, equidistant and unidirectional. For a non-uniform electric field, the electric field lines are not parallel. In a charge-free region, the electric field lines are continuous curves without any breaks.